we are going to take a look at something called Hamilton paths and circuits. So remember, we've already talked about Euler paths and circuits. An Euler path travels every edge in the graph exactly once. I remember these because Euler and edge both start with E. So we talked about those already. Today we're going to look at something called a Hamilton path. So a Hamilton path is a path, or we'll also see Hamilton circuits, and they meet every vertex in the graph exactly once. So remember, in Euler paths and circuits, we could meet edges more than one time, we could meet vertices more than one time. We could cross over the same vertex multiple times. For a Hamilton path, we don't want to do that. We want to travel every vertex in the graph one time. We may not need to travel every edge, but we do want to travel every single vertex in our graph one time. That would be a Hamilton path. And then if I can do that, if I can do that and start and end at the same vertex, that's called a Hamilton circuit. So a path that meets every vertex in the graph exactly one time, but then returns to its original vertex. So technically that first and last vertex we would hit twice. Once at the beginning of our circuit and once at the end. That's a Hamilton circuit. Again, where I start and end at the same vertex. So if I take a look at example 1, we're looking for a Hamilton either path or circuit in each of these, specifically a circuit, Hamilton circuit. So just like with our Euler paths and circuits, we may have more than one option. So if we take a look at A, I want a Hamilton circuit here. That means I need to travel every single vertex in my graph once. Okay, so I'm going to start here. You can start at any vertex you want. And then I'm just actually going to travel along all of these outside edges. I was able to start and end at the same vertex, so I have a Hamilton circuit here. This isn't the only possibility. I could have done sort of an hourglass shape through the middle, or that same hourglass shape but like flipped on its side. A lot of options there. Also notice that we did not travel every edge. These edges in the center we did not travel because we did not need to. For B, same idea. So I'm going to start this time at this vertex. You can start wherever you want. And then I need to be able, again, to travel every vertex in the graph. So I'm going to start by going down this way. That gets me to this vertex. I'll travel up to get this one, and then down to get this other corner here, and then up, and then down, and then back up to my starting vertex. So there I have, again, another Hamilton circuit. Now this isn't the only option. On my keys, it's posted on the website. You can see I have a different path that I took. So even if I started in the same vertex, instead of going straight down, I went toward the center first and then took my circuit that way. So lots of options here. And then for C, our last problem for example 1, we've got this thing that sort of looks like part of a windmill, but maybe like missing one of its petals or blades. So we have couple different options here. We can start at this center vertex, or we can start in one of the blades. So if we start at the center, let's say, I can travel any of the blades. It doesn't matter which one. So if I travel this guy here, I hit that vertex, and now I'm stuck because I don't want to repeat this vertex yet because I haven't traveled the other vertices in the graph. So if I start in one of the blades instead, so let's start here. Start here, can travel to that vertex, travel to my center, travel one of my other blades, and then again I'm stuck because I can't hit this vertex again until I've traveled the other vertices here, but I don't have a way to get there. So this last example actually does not have a Hamilton path or circuit. No Hamilton path or circuit. So does every graph have a Hamilton path or circuit? No. What we're going to look at is if it's possible to tell, like we could with Euler paths and circuits, And then what can we do with these things if they do have them? One of the applications that you guys saw earlier when we did that sort of intro set of problems was that traveling salesman problem. That's an application of a Hamilton circuit. Specifically, it's an application that uses what we call weighted graphs. So you saw in your big salesman problem, New York, I think, is where our salesman started, and he had to travel to all these cities, and you had the distances between those cities. That's what's called a weighted graph. So a weighted graph is a graph in which I have labeled every edge of the graph with a number, and that number we call a weight. It can represent a lot of different things. It can represent a distance. It can represent, called a weight. It can represent a cost. Those are probably two of the most common options. It can represent, again, a lot of different things. And usually our goal is to find the least weight that we can. So what's the path that gives us the smallest sum? And that sum we call the length of our path. And again, usually we want that length to be small. We want that sum to be as small as possible. Here, for example 2, we already have some paths indicated for us. So we can see an arrow traveling 4 this way, and then 2 this way, and 7 this way. Not a Hamilton path because we skipped a vertex here, but just for this path through our graph, our length would be those weights along the edges that we traveled added up. So our length for this guy would be 13. And then for our other graph, we've got 12, we've got 7, we've got 2, and we've got 4. So a circuit here. Still not a Hamilton circuit because we skipped this vertex. But for this particular circuit that we do have, 12 plus 7 plus 2 plus 4 would give us 25 for our length. So this idea is what we need to be able to take a look at that traveling salesman problem. So if we turn the page, we have a smaller example of the same type of problem. So our directions here say, suppose a salesman lives in New York City. So that's where we're starting. On his next business trip, he would like to visit clients in Miami, Los Angeles, Seattle in the most efficient manner possible. So we have to travel to each city in whatever these are, I believe represent plane ticket prices, price for a one-way ticket. So we want to be able to make our trip starting from New York, traveling to clients in each city in a way that is as efficient as possible. So cheapest. What's our cheapest option here? And then remember, of course, that we have to return to our home in New York City. So we have several different options here. And some of these options actually cover more than one possibility. So, for example, let's say we just go around in a rectangle. That would be New York to Seattle to Los Angeles to Miami, and then remember we have to return to New York since that's where we live. This would be the same as if instead of traveling the rectangle this way, I traveled to Miami first and then Los Angeles and then Seattle. So if I took the same thing backwards, the same path backwards, it would end up costing me the same amount because those ticket prices don't change based on which city I'm traveling to or from. So this option, the rectangle option, would be $3.29 for the flight between New York and Seattle, plus $1.59 for the flight between Seattle and LA, plus $3.69 for the flight between LA and Miami, plus $1.19 to get me from Miami back to New York. So that would be a total cost of $976. So that's one option. Another option is that I go from New York to LA, then to Miami, Seattle, and back to New York. So I kind of make an hourglass across the country. So again, that was New York to LA to Miami to Seattle and then back to New York. So our cost for those would be $209 plus 369 plus 439 plus 329. And again, I traveled my hourglass this way. If you went New York, Seattle, Miami, LA, New York, that's the same circuit but in reverse, so it would be the same cost. But this comes out to be $1,346, more expensive, so I'm going the wrong way. So far, this is my cheapest option. We have one more possibility, and it's another sort of hourglass option, but an hourglass flipped on its side. So New York to LA to Seattle to Miami, back to New York. So New York, LA, Seattle, Miami, and then back to New York. And again, I could travel this same hourglass the other way. And this would give me 209 plus 159 plus 439 plus 119 for a total of 926. So this here is actually our cheapest option of the possibilities we've considered, and actually of all the possibilities that we have. This is our cheapest option. But in order to get it, we had to do a lot of guess and checking. And for a graph this size, that's maybe not so terrible. We had 3 options that we looked at, and it wasn't a ton of work, but if there's a faster way to do this, that's what we want to be able to use. Because with 4 vertices to travel between, maybe that's not terrible, but if my graph were larger, if I had 6 cities to travel between or 10 cities to travel between, guess and check could take me a lot of time. So what we're going to use is something called the nearest neighbor method. So unfortunately, we actually do not have a method for finding a Hamilton path or circuit that's going to be the most efficient method every single time. We actually don't even have a way to be able to tell if a graph definitely will have a Hamilton path or circuit for sure just by looking at the graph. We could with Euler paths and circuits, we could look at the degree for those vertices and tell it's going to have a path, it's going to have a circuit, it's not going to have anything. We can't do that for a Hamilton graph. But what we can do is use something called the nearest neighbor method that will give us a pretty close approximation of the most efficient path. Now, it's not going to be perfect every time, but it does work fairly well. And so anytime I'm asking you to find an efficient Hamilton path or circuit, your directions are going to include use the nearest neighbor method. That's what I want you to do. Okay, with the understanding that if it's not actually the most efficient path, that's okay. I want you to use this process rather than do a bunch of guess and checking. So here's how the nearest neighbor method works. So you need to actually have a complete weighted graph. So something like this where you have every single edge possible and they're all labeled. All their weights are on your graph. So when you have that, start wherever you need to start. So for these like traveling salesman problems, our salesman was in New York, so we needed to start in New York. If your directions say start at vertex A, start at vertex A. Okay? And then to decide which edge to travel, which vertex to go to next, you're going to pick the edge that has the smallest weight. So you're going to travel along the edge with the smallest associated weight. Okay? If there's more than one edge of minimal weight, your official directions are choose at random. And this is why this system isn't perfect. So even if you and your neighbor both follow the sort of algorithm or this process perfectly, if you make different choices for those choose at random moments, you may end up with a different length for your paths at the end of the problem. That's okay. Once you get to that new vertex, do the same thing again. For your options that you have left that will take you to a new vertex, pick the edge with the smallest weight. Once you've been to every single vertex and you're ready to go back to your starting place, again, choose the edge with the smallest weight that will take you back to that starting vertex. So here's what this looks like. So we are finding our nearly minimal Hamilton circuits based at vertex A. So I'm going to start and end at A. Okay. So my nearest neighbor method says start by traveling to the vertex that will be the smallest weight to get to. So travel along the edge with the smallest number. My options are 8, 3, 4, and 1. I'm going to pick 1, and then I'll just keep track down here. Now from B, I don't want to go back to A yet. I need to go to a new vertex. So my options are 5, 4, and 6. 4 is the smallest, so I'm going to go 4. From here, the only new vertices are E and C, so 7 or 3. 3 is smaller, so I'm going to go 3. Now, I actually don't have a bunch of choices. I have to go to E, which means I have to travel this edge that's 8. Now I've been to every vertex in the graph. I need to get back to my starting point, so I am again going to travel this edge that's 8. And then find the length of your path by adding all these up, and you get 24. Is it possible that there's a Hamilton circuit in here whose length is less than 24? Yes. Do I want you to have to spend a lot of time guessing and checking to figure that out? No. Use the nearest neighbor method. Particularly when we get to larger graphs, like example B here, there's a lot going on. Guessing and checking every single possibility would take you forever. I don't want you to take forever on this. I want you to use the nearest neighbor method. So again, we're going to have a path based at vertex A. Right now, our options are 6, 3, 2, 3, and 10. Our smallest option is 2, so that's what we're going to travel. Now our options are 3, 6, 4, and 3. 3 is our smallest option, but we have 2 possibilities here. Okay, you can pick either. Your official directions are choose at random, so pick whichever one you want. I'm going to choose this 3, but I will show you what our path would look like if I had made the other choice. So from here, I can go to B, I can go to E, or I can go to F. I don't want to choose this option because that takes me back to A and I'm not ready to get there yet. So our options are travel an edge that's 9, travel an edge that's 5, or travel an edge that's 2. So I'm going to travel the edge that's 2. Now I still need to go to F and B, so my options are 4 or 7. 4 is smaller, so I'm going to make that choice. Now I still need to go to B, so this is the edge I'm going to travel. That's 6, so plus 6. And then my last step is to complete my circuit, get back to A, so I have to travel the edge that's 10. So this would give me 5, 6, 7, 17, 27. If I had made a different choice here between my 3s, if I had traveled this instead, that would have impacted the rest of the choices for my graph. I still would have traveled this 2 next, but now at C, having to go to either B or F, I would have had a different choice to make. So let me show you what that looks like. Here's the other option. I had gone 3 up first. I would have gone 2, and then traveled to 5, and then traveled to 6, and then traveled to 10. So some of the end of my graph looks very similar, but I actually got different final lengths for my paths. It's okay if you get a different final length than someone else because you made a different choose at random selection. That's okay. I know for some of these graphs that's a possibility. That's okay. So now let's take a look at that traveling salesman problem again. Okay, here's the one that you guys had in your sort of intro set of problems. Now, the issue with real life is that we don't always have a complete graph. There's not necessarily one direct road that will take you from New York to Detroit. We are likely going to have to pass through Buffalo or Pittsburgh first. So we have to account for that as we look at these real life scenarios, okay? But we know that our salesman starts and therefore must end in New York. So we're going to use our nearest neighbor method to figure out a nearly minimal Hamilton circuit here. So from New York, my shortest distance here is Washington. So I'm going to go from New York to Washington. That's 248 miles, I believe, is what this represents. And then from Washington, our options are 421, 259, 427, or 374. Again, pick the smallest option. So from Washington, we're going to go to Pittsburgh. Washington to Pittsburgh, since that's our smallest option. So plus 259. Now from Pittsburgh, we can go up to Buffalo, that's 224, down to Charleston, that's 229. We can go to Columbus, we can go to Detroit. Those are our options. We don't want to go back to New York just yet. Our shortest path would be the 187, so we're going to go to Columbus. Columbus. So that means we're going to have to add 187 to the length of our path. And now from Columbus, we got to figure out where to go. So from Columbus, our shortest option would be to go to Cincinnati, right? Out of 206, 111, and 211. 111 is the smallest, so that's where we're going to go. We're going to go to Cincinnati. So that means we add 111. Now from Cincinnati, we can go directly to Detroit or Charleston. We're going to go to Charleston since that's the shortest option. So we're going to go to Charleston, which adds 253 miles to our trip. And now I want you to notice, again, this is a real life problem, so it doesn't fit perfectly with what our like theoretical graph theory instructions say. At this point, I can't get directly to either of the other cities, so we're going to have to travel through somewhere. So to get to Detroit, I think my shortest option would be to go through Columbus to get to Detroit, or to get to Buffalo, I could go to Pittsburgh and then to Buffalo. 206 and 211 is smaller than 229 and 224, so we're going to go from Charleston through Columbus to Detroit. Now, I know that technically breaks the rules, but again, real life doesn't always fit with our theory. So this would be 211 plus 206. Then from Detroit, we're going to go to Buffalo. So Detroit to Buffalo, which would add 249 miles. And now we've been everywhere in our territory, and we can go back to New York. So from Buffalo to New York, and that adds 430 miles onto our trip. So if we add all this up, we get 2,199 miles. Again, we had to cheat a little bit, but sometimes, again, real life doesn't quite match up with what our graph theory says. Those are Hamilton paths and circuits. Your homework is on the next page in your packet. Please notice, just like with your Euler homework, that there's a section of problems that say choose one. So you're finding, again, a mail route here. These are all your options. You only have to do a mail route for one of them.